Hey, welcome to my favorite video. Maybe I shouldn't pick favorites, but this would be uh, way up there. Top two anyway. And the topic is solving exponential and logarithmic equations. And that's what we'll do. Exponential ones and logarithmic ones. These are ones that you may not have ever seen before in solving exponential equations. So if I have 2 to the x is equal to 9, how do you solve that? Um, we've solved things if they're 2x is equal to 9, or we've solved x squared plus something, and we know how to deal with quadratics. But when I have an exponent up there that is a variable, that's a different kind of thing. So we'll look at strategies for solving those, and in addition to logarithmic equations. So a couple things that are in play here, tools that we can use. Of course, any of the exponent laws, those are all things that we need to be able to manipulate a little bit, and in addition, the logarithmic rules. Probably one of the most powerful ones is switching in between exponential and logarithmic forms. And we'll see that doing that helps us solve either exponential equations or logarithmic equations. But we need to be aware of all of these other things that we can do. So let's try just a number of different equations. First one. Here I've got 5 to the 4x minus 7 is equal to 125. I notice right away that my exponent has a variable in it. And so I have to implement strategies that I typically don't do when I'm solving an equation. And one of them, as I've indicated in the title of the slide, is to use the same base. So I look at 125 and it sort of sticks out like a sore thumb because 125 is 5 cubed. So on the right side, instead of 125, I have 5 cubed. Now we can use that idea that if the bases are the same, for these two to be equal, the exponents must also be the same. And so I can just write the exponents down by themselves. Since the bases are the same, 4x minus 7 must be equal to 3. And then solve that equation. 4x is equal to 10, x is equal to 10 over 4, or 5 halves. It's a good idea always to go and check your answers as well. Let's just do a quick check on this one. So 5 to the 4 times 5 over 2 minus 7. We want to know if that's equal to 125. Notice I went right back to the original equation, not to anything that I wrote down, but right back to the original. 4 times 5 is 20, divided by 2 is 10. 10 take away 7 is 3. So on the left side I get 5 cubed. Is that equal to 125? Certainly. Checks out. So one of the strategies then that I can use is if the bases are the same, I can equate the exponents. Now, what happens if the same base thing doesn't work? So 4 to the x is equal to 9. I can't express 9 as a power of 4. 4 squared is 16. 4 to the first is 4. Not going to work. So what are some things that I can do? Well, I can use maybe change its form. Maybe I can change this form from exponential form to logarithmic form. What would that look like? Well, x is the exponent is equal to log, my base is 4, of 9. Hey, that's not too bad. So my answer, x, the exponent, is equal to log base 4 of 9. But now I've got a problem that on my calculator I don't have log base 4. But I do recall the change of base formula. Change of base formula simply said log the value and divide it by the log of the base that you were using. And the change of base formula says I can use whatever base I want. I'm choosing 10 because that's on my calculator. So now simply on my calculator I go log 9 divided by log 4 and I'll come up with my answer. It should be 1 point something or other. Okay, so that's how I could solve that one. We'll see in a second that there's other strategies that we could use as well. Now let's take a minute just to look at this other strategy, and it's called the property of logarithmic equality. It's sort of like, remember when you have something like x squared is equal to 16. If for me to solve for x, I square root this side, and I can square root that side. Or if I have 2x is equal to 10, I divide both sides by 2. So what I do to one side, I have to do to the other side. I could do that same thing with logarithms. So like in this case here, if I have log base a of 25 is equal to log base a of 3x, that's the same thing as 25 is equal to 3x. Notice I have logs on both sides, and then to solve this equation, I simply dropped those two logs. If they're on both sides, I can do that. The other way of doing that is something like this. What if I had an equation that looked like this? 4x is equal to 9. Recognize that one? What I could do is I could log both sides. So I could bring in my own log. And let's use log, I guess it doesn't matter what log we'll use. We'll just use log base 10. So let's log this side. And I can do that as long as I log the other side. Now you're probably wondering, well, why in the world would you throw logs in to an equation that doesn't look too bad? Well, I do that because now look where my x is. It's in the exponent. And remember that old power rule? I can bring that x out front. Now it's x times log base 10 of 4 is equal to log base 10 of 9. X now is no longer an exponent, it's out front. It's where I can get at it. Now I'll divide both sides by log base 10 of 4. Log base 10 of 4. And I can do this on my calculator. It'll come out to 1 point something or other. If I look back to the other slide, and using that change of base, or changing from exponential to logarithmic, and then using the change of base formula, notice I came out with the exact same answer. Okay, so if I have an exponent that is a variable, one nice little trick is to use the property of logarithmic equalities, which says I can log this side as long as I log the other side as well. Let's try some other equations. Here's one where it's set up perfectly to do that. I have an x in the exponent, so let's log this side, and we'll use log base 10 of 3 to the x, and I can log that side as long as I log the other side. Again, I'm using base 10. Use the product or the power law to bring that x out front. X times log 3 is equal to log 20. Divide both sides by log 3. So I'll get log 20 divided by log 3. And when you do that, your answer comes out to 2 point something or other. Okay, let's try another one. Oh, here I've got one where, again, I have a variable that's in the exponent. This time, though, my base is e. If my base is e, it makes sense for me, because I can pick whichever one I want, but it makes sense for me, instead of using log base 10, to use log base e, which we simply call ln. So I'm going to ln this side, and I'll ln this side. Using the power rule, I can bring the minus t out front, and then I have times ln of e is equal to ln of 0.04. But remember what ln of e was? Ln of e was always just 1. To what exponent must I raise e to get e to the first? It's just 1. So ln of e is simply 1. And so now to solve for t, I'll divide both sides by -1, and I'll get ln 0.04 divided by -1. So I'll do that up on my calculator and see what I come up with. The trick was that if my base was e, I'll ln both sides. Let's try another one. This one, it looks like I'm wanting to use this property of logarithmic equality. I'm not sure why I put an O there. It's at E. Anyway, I can do the same thing. So let's log both sides. I don't have base E, so I'll just use log base 10. X plus 2 is equal to log base 10 of 4 to the 1 minus x. Use the power rule and bring that x plus 2 out front. Have log 5, use the power rule to bring the 1 minus x up front. And now I've got an equation where the variables are all where I can get at them. I'll determine what the log of 5 is, point whatever, use the distributive law to multiply it through there. Same thing here, figure out what the log of 4 is on my calculator, distribute it, collect x's, and solve. Okay, but the trick there was if I see a variable up in the exponent, I can log both sides and then use the power rule to bring that out front where I can get at it. Okay, here's some other equations. Some ones a little bit more simple, but these are ones where I can try different things. It's already a logarithmic equation. Maybe let's change it to exponential form. We can try different things, but one of the obvious things that you want to try, it may not be obvious, but one thing you want to try if you have a logarithmic equation or an exponential one is to swap forms and see if it makes sense. This one is saying to what exponent must erase 5, or what exponent must erase 5 to get x. That exponent is 4. Looking at it in log form, it's hard for me to look and say, oh, the answer is this. But if I change this to exponential form, base is 5, exponent is over here is 4, is equal to x. Suddenly, it's all clear. Now this is an easy question. 5 to the 4th, do it on my calculator, and I'm done. When I'm looking at it in log form, I was struggling to find exactly what I should be writing. I guess I should have read it as 4 is the exponent to which is 5 is raised in order to get x. And that's exactly what we wrote for exponential. Same thing here. I have a log form. If you want to always rewrite the ln as log base e, that's perfectly acceptable. Now to change this to exponential form, e to the minus 2 is equal to x. There I go. Now all I have to do is solve. Remember that e is a number, and on your calculator you probably have an e to the x button. You just use that button there and say e to the x, and the x is a minus 2 is equal to, and you'd come up with your answer. Probably 0.2 or somewhere like that. Okay, couple last equations. Ooh, this one looks a little bit bigger. Log base 5 of 8 minus 7x is equal to 3. It's still in that same logarithmic format though. Why don't we try and change it to exponential format? Base is 5, exponents 3 is equal to 8 minus 7x. Now this is just a regular equation. 5 cubes 125 is equal to 8 minus 7x. I'm going to move the 7x to this side to make it positive. Move this to the other side. That would be about negative 117, I think. Divide both sides by 7. Negative 117 all over 7. And when I divide that, it comes out to 116, is it? 6 and 5/7. And it'll be negative. Or you can use the decimal equivalent of it as well. But the key on it, all this stuff here is math that you've done forever. But this is the trick. This is in this course, this is what we're looking for, is to be able to change from log form to exponential form. That's the key thing. That's where all the points are worth. Then after that, it's simple algebra of solving it. Let's try one more. Oh, this one is different. Notice on this last one, I have just one log is equal to a number. But in this case, I've got two logs together is equal to a number. That's different. I wonder if there's a way maybe that we could combine these two. I think back to some of the properties we've looked at before. Let me just look quickly. Right here, this is the one I'm wanting. It looks like I have two logs together just like this one, and I can combine them into one using this product rule. Okay, let's go back. So I can combine these two using the product rule. So it'll be log base 2 of the product of x minus 4 and x minus 3. X minus 4, x minus 3 is equal to 1. So there I've combined these two into one logarithm. Now I can switch form. Here's my base. 2 to the exponent of 1 is equal to x minus 4 times x minus 3. Now I can FOIL this out. Looks like we're going to get a quadratic, but I have to make it equal to 0, all quadratics, right? So let's FOIL this out. X squared minus 7x plus 12 is equal to 2, and let's make that 0, and let's slip the 2 over to the other side and subtract it, so I get 10. Now I've got a quadratic equation. I solve that with my quadratic tricks. I think I can factor this one. I think it's x minus 5, x minus 2. Will that work? X squared minus plus, yep, is equal to 0. So in order for this equation to be true, x must be equal to 5, or x must be equal to 2. Well, that's good. That's a nice one. I used the product rule to put these together. I switched its form, so this was the product rule. Then I switched form from log form to exponential form. And then I just solve things like the normal algebra. One thing that you want to always do, though, is at the end is check. We checked one of our answers. We probably should have been checking all, but let's just go back and check. Let's maybe check the 2. Let's plug in a 2. Okay, so plug in a 2 right here. 2 take away 4 gives me a negative 2. Hold the horses. Hold on here. I can't take the logarithm of a negative number. 2's not going to work. Cross that one out. Won't work, so it doesn't check. Let's try 5. Will it work? 5 take away 4 is 1. Yeah, that's okay. 5 take away 3 is a 2. Yeah, that's okay. And if I follow that one through in checking, it certainly will come out. Okay, so those are most of the examples of types of equations that you can get with logarithms. Keep in mind all of the different tools that you can use. So the exponent laws are in this same base law. That's a nice trick. The product, quotient, power rules are in. You can use the product or quotient rules to get two logarithms together on a side. The power rule is quite useful if you have an exponent, which is a variable. Power rules is quite nice that you can log both sides using that property of logarithmic equality. So keep all those rules in mind as you're looking at any logarithmic equation. And if you have any questions, of course, always ask your instructor.